Now let's talk about uh, the vector model of an atom, and in this case, we will be considering only the atoms having one electron in their valence shell. So if we take an example of, let us suppose, if I talk about hydrogen. So for hydrogen, what I have is 1s1. So the valency of hydrogen atom is 1. Now, if I take another example of, say, for example, lithium. So what will be its electronic configuration? It will be 1s2 and 2s1. So the inner orbit is filled in case of the lithium, and its valence shell has one electron. And if we proceed for another example, say for example sodium, in case of sodium, it is 1s2, 2s2, 2p6, and 3s1. And we have we have 10 inner orbit electrons and one valence electron. So so these kinds of atoms, we call them as one electron atoms, and uh, and the valency of these of each of these atoms is equal to 1, and this electron, the electron that's in the valence shell, this electron is also called as optical electron. and and it's this electron which interacts with light, and we are not interested in dealing with the properties here. What's our intuition here is basically to calculate the LS coupling, to calculate the total angular momentum of this electron, which is present in the outermost shell of an atom. And if we go in a very clinical way, we would say that in an atom we have an electron, and this electron has orbital motion, and 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 due to the orbital motion of this electron is linked with orbital angular momentum. And uh, let me assume that this orbital angular momentum is L vector, and at the same time, this electron has spin angular momentum associated with it, because this electron has it has a spin, and this spin was experimentally calculated by and predicted by Gaudsmith. And so it has spin angular momentum because it has the intrinsic spin, and hence it has the spin angular momentum S. So if I have to calculate the total angular momentum of this electron, that's that's present in the atom. This its total angular momentum will be the sum of angular momenta of the inner orbit electrons. If I take an example of lithium, okay, so we have completely filled orbitals, and we have partially filled orbital. And in case of completely filled orbital, I assume that the vector sum of the angular momenta of the closed orbitals for lithium is given by Li, and the angular momentum, the orbital angular momentum due to this optical electron or this valence electron is Lv. And similarly, we will have the same situation for spin angular momentum. But what is important here is that in the closed shells, this sigma Li will be equal to 0. Or in other words, I would say that the vector sum of the angular momenta due to the inner orbit electrons cancel out, and the total orbital angular momentum due to these closed shells, the shells that are completely filled, is equal to 0. And same is the case with the spin angular momentum, SI plus S SV. So the vector sum of the spin angular momenta of all the inner electrons, where the octets are completely filled, their spin angular momenta is the vector sum of their spin angular momenta is 0. So, so what are we left with here when we have to calculate the total angular momentum of the electron, the valence electron? It automatically means, if I say the total angular momentum of the optical electron, it automatically means the total angular momentum of the atom itself, because the angular momenta of the electrons that are there in the closed shells where the octet rule is complete, their net or resultant angular momenta and spin angular momenta add up to 0 vectorially. So, so this is the case. So now this angular momentum, if we go back to the problem of hydrogen atom, what this angular momentum is basically, it has quantization. It's quantized, and the value of this angular momentum is under root of L times L plus 1 H cross, where this L, this small l, is the orbital quantum number. Or we could say orbital angular, that will be more precise, orbital angular quantum number. And this L can have the values 0, 1, 2, and so on and so forth to n minus 1, where this n refers to the principal quantum number. And this 0 refers to S, this 1 refers to P, and this 2 refers to D, so on and so forth. Now, that's not the point of contention here. What's important here is that this angular momentum is quantized, and this L can have a different set of values depending on the value of the principal quantum number. And at the same time, if the magnetic field is applied along the z direction, in that case we can write down Lz. And this Lz will be MLH cross. And this ML is it is orbital magnetic quantum number. And this ML can have the values equal to 2L plus 1. Or we can say the values for ML will range from minus L to 0 to plus L. Now, talking about the magnitude of spin quantum number, so in analogous to the orbital angular momentum of this electron, we have spin angular momentum equation for spin angular momentum. So for spin angular momentum, what I have S is under root of S times S plus 1 times H cross, where this S is spin angular momentum quantum number. And this S can have the value equal to 1 by 2. Now, if I take the value of S equal to 1 by 2, what am I going to get? The magnitude of this spin angular momentum will be under root of 1 by 2 times 1 by 2 plus 1 h cross. So this is 3 by 2, so this is 3 by 4, so this is under root 3 by under root 2 whole square, and root will cancel, so 2h cross. Now, talking about the z component, of spin angular momentum, that is sz, and that's going to be msh cross. Okay, this ms can have the values plus minus 1 by 2. All right, so if we take the z component of magnetic field in this direction, say for example this is pz, we will have one value, and we will have another value, and this will correspond to h cross by 2, and this will correspond to minus h cross by 2. All right, now after this, we'll be talking about the total angular momentum of this one electron atom, and this total angular momentum, total angular momentum. This total angular momentum is symbolized as J, and this total angular momentum is the vector sum of orbital angular momentum and spin angular momentum. So what we have here is we have spin orbit interaction, and this spin orbit interaction leads to the resultant total angular momentum, and this total angular momentum, by analogy, this total angular momentum can be written as under root of j times j plus 1 h bar, and this j, this small j, we call this small j as inner quantum number, or it's also called as total angular momentum quantum number. And under similar considerations, we'll have the z component of this j, and that will be mjh cross. Now, what is this mj? This mj is magnetic total quantum number. All right, and this mj can have 2j plus 1 values, or I should say that the values for this mj, they will range from minus j to plus j. If we start from the left, every time we have to add the unit to reach to plus j. And we can have this what we call as the z component of this total angular momentum. We can write down this jz as the sum of the lz plus minus sz. And this mg that we have, if I write it in terms of the z components, what I'll have mg h cross will be ml h cross plus minus ms h cross, and h cross will cancel from both the sides. So what we will have is this mj. The total magnetic quantum number will be the orbital quantum number, the magnetic orbital quantum number plus minus magnetic spin quantum number. And what is important here is that suppose this ms is plus minus 1 by 2. And if I take a case of, say, for example, L is equal to 2, in this case, ML will have 2L plus 1 values. So this is 4 plus 1, that's 5. So the values that this ML will have will be minus 2, minus 1, 0, 1, and 2. And what we have here is what's the maximum value for MJ? The maximum value for MJ is certainly plus J. What's the maximum value for ML? Its maximum value is plus L. And what's the maximum value for spin magnetic quantum number? That's equal to S. So this J that we have is L plus minus S. Now, taking the example of L equal to 2. Now, if I take this L equal to 2, what I will have here is J will be 2 plus 1 by 2, and this will give me, this is going to give me, so L equal to, taking L equal to, let me take L equal to 1. For the sake of simplicity, so this will give me 1 plus 1 by 2, so this is 3 by 2. And if I take the value for S equal to minus 1 by 2, so in that case I will have the value of J 1 minus 1 by 2, that will be equal to 1 by 2. So this is how we can add the quantum numbers to get the total value for J. Now, if I take another example, say for example for L is equal to 0. Now, if I take L is equal to 0, now J, in one case, its value will be 0 plus 1 by 2, so this will give me 1 by 2. And for another case, J will be 0 minus 1 by 2. This will give me minus 1 by 2. But the total angular momentum quantum number cannot be negative, right? So here the value for J is simply 1 by 2. Now, the point is that what we have is we have to add up the vectors vectorially. Now, if I assume that this is a vector L and I have another vector S, and the third vector will oppose L and S, so I can write down then this J vector in view of triangle of vectors. This J vector is L vector plus S vector. And there always exists an angle, so we can have an angle between L vector and S vector. Now, assuming this angle to be theta, and let's put a subscript here as LS. And if I take the dot product of this equation, if I write down J vector dot J vector is L plus S vector dot L plus S vector. Now, what is the intuition here is that we want to calculate the angle that's there between the orbital angular momentum and the spin angular momentum. Now, in order to calculate that, what we have done is we have taken the dot product. Now, this will simply give me J square, and L will give me L square, S and S will give me S square, and then I'll have L dot S plus S dot L. Since the dot product of vectors is commutative in nature, so we can write down 2L dot S. Right. And we can boil down this equation as J square is L square plus S square plus twice LS cos theta LS. So from this equation, I can calculate theta ls. So this cos theta ls will be J square minus L square minus S square divided by twice ls. And we have already written down the value of J square, L square, and S square. So we'll put down those values here, and we'll be able to calculate this theta ls, which has to be constant, And what will be that? That will be cos theta ls is, for J square, it is J times J plus 1 minus, for L square, it is L times L plus 1. Everyone has H cross with it. I'll put that at the last, and minus S times S plus 1 and H cross. Divide by 2. L is under root of L times L plus 1. H cross is out. And S is S times S plus 1. H cross is out. Now here I have H cross square. Now this H cross square and H cross will cancel, and we can have cos theta ls is J times J plus 1 minus L times L plus 1 minus S times S plus 1 divide by twice under root of L times L plus 1 under root of S times S plus 1. All right. So from this equation, we can calculate the value of theta ls, and with the same procedure, we can find out the angle between S and J. We can also find out the angle between L and J. And to go with the geometrical interpretation of this problem, what we have is we have orbital angular momentum. Let me draw it here. Okay, we have orbital angular momentum, and this is L vector, and then we have spin angular momentum, and that's S. And this L and S, they adapt vectorially, and they give us J. And both of these, this S, now this is my S. Should I go? I would like to go like this. So this is my L. Let me go like this, and this is my S. Now, what happens is that both L and S, they have a constant angle, that's theta ls, that can be calculated from this equation. Both this L and S, they precess towards the total angular momentum J. So this is our spin orbit interaction. So L and S, they interact vectorially, and they precess, L and S precess towards the total angular momentum J. Now, if we have the same situation in presence of a magnetic field, and this magnetic field is applied along the direction, so what's going to be the situation like? So if I assume this is my L, and this is my S, and they have a resultant, and that resultant is J, right? And this J, now what are we assuming? We are assuming the magnetic field in the direction of Z. So this is BZ. Now, what happens in this case is that we have the precession of spin angular momentum and and orbital angular momentum. The spin angular momentum and orbital angular momentum, they vectorially they press towards, they precess towards the total angular momentum j. But at the same time, this j precesses towards the applied magnetic field. And what is assumed here is that this magnetic field is applied along z direction. So talking in a very categorical way is that we have a precession of spin angular momentum and orbital angular momentum towards the j. Uh, uh, as was the case in spin-orbit interaction, where there was no presence of external magnetic field. But here we have the same situation. But in addition to that, what we have is that this j, this total angular momentum vector, it precesses towards the z component of towards the z direction of applied magnetic field, towards the magnetic field. In this case, the magnetic field is applied in z direction, and this becomes the basis. This becomes the basis for the explanation of Zeeman effect. The splitting of spectral lines in presence of magnetic field. Okay, goodbye.